Hi, in today's video, we'll be continuing our journey into discrete mathematics. And now, we'll start learning how to prove theorems or statements. Firstly, we want to know how to prove conditional statements. There are many examples and you must try them in the book that is provided in the description, because only when you do math and struggle with it, then you'll understand how you should think about proving certain problems. But in this video, I'll teach you how you can process your thought and have a starting point on how you want to prove a theorem. Let's begin. We first need to note what are definitions. These are the statements that have been defined to be true unambiguously. So these are like your starting points in any context. For example, you say that n is even if and only if 2 divides n. Because it is defined to be true unambiguously, this is an if and only if statement. So if 2 don't divide n, then n is not even. Something like that. So when we want to prove conditional statements, we start out with either known propositions or the definitions or even the axioms from the ambient theory. And this will allow us to deduce new information about each statement so that we can reach our desired goal. So, if the statement is if P then Q, we want to suppose we have P already. So, given that this is true, what we want to prove is Q is true. And so we use whatever we know to get a deduction of Q. And this is actually a form of modus ponens, a logical inference that was covered in the previous video. Let's take a concrete example. We want to show that if x is odd, x squared is odd. And so, we suppose that x is odd. Now, by the definition of an odd number, we start. Then we will square it. And we'll reach the definition of an odd number again for x squared. And therefore, this proves that x squared is odd. So you can see how this is a very direct proof of proving conditional statements. Now, we move on to a less direct one. In this case, we want to prove the conditional statement by breaking them down into cases so that the problem is easier. An example will be shown. For example, the conditional statement, if n is a natural number, we want to prove that it is a multiple of 4. But we are unable to determine more information about n. So in this case, we break them down into cases so that they are so the number is either even or odd. The first case is that it's even, and the second case is that it's odd. By doing so, now we have the definition of an even and odd number, and we can use it to prove that it's a multiple of 4 in either cases. And so, this is one way to use proof by cases to prove a proposition. Sometimes, when there are 2 or more variables, there's a symmetry to the proof. For example, in this case, m or n are integers with opposite parity. So either m is even and m is odd. But it will just be the same proof as saying n is odd or n is even. And so, usually mathematicians would like to use the word without loss of generality to reduce the length of the proof, and we only need to prove one case and the other case is similar. A next way of proving a conditional statement is to prove a logical equivalence of it. We have seen that a logical equivalence is the contrapositive of the statement, where we prove that not Q implies not P. And so this might be easier because our conclusion Q might have more information to work with. So consider this proposition. If 7x plus n is even, then x is odd. To do this directly, you suppose that the antecedent the hypothesis is true, and you work out to get x is odd by the definition. But if you had done the contrapositive, it might have been easier because now you know that it's not odd, and you just want to manipulate to get 7x plus 9. And so, using the different techniques in proving requires experience, and doing more problems will definitely help with that. So I encourage you to do the problems in the book. Another way to prove things is to use contradiction. Suppose a contradiction is something that's always false. So what you do now is you suppose that you have not P. Then it will lead to a contradiction, and this means that not P is false. And as such, this means that P, the original statement, is true. So remember that if not P is false, P will be true. And so the idea of contradiction is that you are able to get more knowledge by assuming something is true, or something else is true, and that can lead to a contradiction. This is a very classic example where we want to prove that the number square root 2 is irrational. But the definition of irrational is just not rational. And so it's very hard to work with it. And hence we want to use a contradictory proof by assuming that now it's rational. We have the definition which gives us more information, and we work out to prove a contradiction. As the author said, we appreciate the power of the proof of contradiction as we had no initial assumption, or we do not know where to begin with the number square root 2. And so by assuming the proposition does not hold, it allows us to reach a contradiction with proof that the proposition holds. We can apply this to conditional statement too, because the negation of not P and Q, the negation of P implies Q is equivalent to P and not Q. As you can see, now we have two pieces of information, P and not Q, and so it might be easier to reach a contradiction or somewhere else with more information. Next, we want to prove biconditional or equivalent statements. What does that mean? Remember that biconditional means P is equivalent to Q, meaning you want to prove P implies Q and Q implies P. So you need to prove these two in order to prove the entire biconditional. And if you want to have more statements to prove at the same time, for example the equivalence of P, Q and R, you can actually just do a circular proof. Not a circular argument, but a circular implication, where P implies Q and Q implies R and R implies P. This will show that all these statements are equivalent. Next, let's move on to proving quantified statements. And the first will be the universal statement. So a universal statement is of this form: for all x in X, Px holds. So what you want to do is you want to assume nothing about the x and use a general x. So now we say that we are given an x, we just need to prove that Px is true. And since this x had no other assumptions, it means it works for any of the x's, and hence Px is true for all x. Sometimes maybe it's hard to do so, and you want to use a contradiction, and it's fine. And so you can see how the previous examples of proving techniques allows us to mix and match to prove harder statements. Similarly, to prove accidental statement, we need to find a specific example such that it holds, because that is what is required of the proposition. Finding a specific example can be a constructive proof as follows. It can also be a non-constructive proof where you don't really find a real value of x, but you assume this value of x has certain properties in either case, and you are able to construct something out of it. But that's really more of a non-constructive, and doing more examples will show you and make you understand how to use different constructive and non-constructive proof better. You can also prove it via contradiction, like I always say, because it gives you more information. And one thing to note is usually in mathematics, when we are proving accidental statements, it comes with some sort of uniqueness at times. And this means that there is only one particular example that works. And so how does it go is, after we prove existence, we assume that another example has this particular property, and we show that they are equivalent. They are the same answer. So x1 equals to x2 basically. Lastly, we move on to disproving statements. And actually everything we have done is to learn how to prove the statement, but disproving is essentially just proving the negation of the statement. And that is the only way to disprove a statement. If we want to disprove a universal statement, what we need to find a particular x with a property that holds. If we want to disprove an implication, we need to produce an x such that px is true and qx is false. These are known as counterexamples. But you can also disprove a statement via contradiction, where you assume that the statement is true and it leads to a contradiction. But you can see all these are just proving the negation of the statement. And so, if you want to disprove a statement, you have to prove its negation. I hope you have understand more about proving techniques and how you want to apply them. But the main point is that once you know these techniques, it just gives you a starting point. You need to do more examples and exercises in the textbook to understand better when and where you should apply different proving techniques. And sometimes it's just about applying one technique, failing, not giving up, using another technique, and carrying on until you prove the statement. Thank you for listening, and I hope you have enjoyed this video.